Okay, class, this is lecture 10. A couple bookkeeping items to begin with. So the midterm obviously was a bit of a kerfuffle this week. I think overall people did quite well on the parts that I've actually marked so far, the true, false, and the multiple choice. I've decided that questions 29 and 30 are going to be bonus questions, so your marks will be reevaluated, taking those two questions out, and then anyone that gets those right will get bonus marks. 29, there's only, I think, about 5 or 6 people, maybe 6, I think, that got the answer. So obviously there was something missing from my end in terms of teaching the material. So what I've decided to do is add a question to the problem set, the third problem set, that actually helps to consolidate the information that was requested really in that particular question. Some of you have asked for the answers to questions. I can't give those yet because not everyone has written the midterm due to conflict with the Thursday rescheduling. Those individuals will be writing this week. As soon as that is done, I will make the answers available, and you'll see sort of where the what the right answer was, obviously, and where the question was coming from in terms of 29 and 30. Yeah, people did quite well otherwise. So, okay. Then a couple other things. So assignment 1 will be marked by the middle of the week. I'm hoping, probably that's a reasonable target. Assignment 2 is due on the 28th, which is this Thursday. And we also have our quiz on that day. It'll be from 1:50 to 2:20. There will be a session before that. There'll be an asynchronous lecture, and we'll have a synchronous period before the quiz. The quiz will cover the lectures, I think, from 6 until the Tuesday lecture. So lecture 11, and but you should focus your attention on the last 3 lectures on the electrophysiology, okay? And there'll be a new problem set available this week. Hopefully I'll have that up by Tuesday or Wednesday. And as I said, I'm going to add a question related to the question that wasn't handled very well, I thought, in terms of the midterm. Okay, so let's get going on lecture 10. Some of the stuff I'm going to talk about is actually in Stein's book. Most of what I'm going to talk about, though, is not. And you'll see if you're following along in that book, as we move along and start to talk about a little bit of the molecular structure, you'll see I'll start to follow his book for a piece. But then we'll digress and diverge again from his textbook. And so anyway, so I'm going to start this lecture by reviewing what we did in lecture 9, because that material is actually very important. And I'm going to review 3 things. I'm going to review the idea that the force that determines whether, ions are flowing across the membrane inside or moving in or moving out is dependent on the difference between the membrane potential, which for Van 't Hoff's law would be the equivalent of the difference in hydrostatic pressure, versus the magnitude of the term that's derived from the mass action diffusional gradient, the gradient in concentrations, which we refer to here as EREV. That's called the reversal potential, the equilibrium Nernst potential. And it's that difference that's going to determine what direction ions actually flow. And when these 2 terms are equal, that is actually equilibrium. Okay, and we'll make that point again today. I'm also going to highlight once again this notion that lipid bilayers are actually capacitors. And so what that means is that the membrane itself, without channels, does not allow ions to pass through, but it will allow storage of charge and allow the cell to have a net positive or negative charge. And we'll see that that's exactly the equivalent of what happens in an electrical circuit with a device called a capacitor. Okay, and then we'll also highlight again or emphasize again the conventions. Things are a little bit more complicated when we talk about ion flow than, for example, water flow, because we can get negative ions flowing into the cell or out of the cell, or they can be positive ions flowing in and out of the cell. And so we need to have some conventions, and I'll review those conventions. And then we'll talk a little bit about some techniques that are used in electrophysiology, so you can appreciate when I'm showing you some actual recordings, you'll get some idea of how those were actually made, those particular recordings. We'll start to apply some of the ion channel equations and start to use the conventions and the understanding of what determines flow. And we'll start to actually look at a couple different types of problems, such as, what causes an action potential, as an example. And then we'll get into really the sort of meat of talking about ion channels from a functional standpoint. And we're going to introduce the concept of channel gating. And this really is brings us back to the concept of isomerization, and this idea that there are chemical kinetic equations that we need to understand and think about when we try to understand this process of channels actually opening and closing. As we're going to see, channels are not opened all the time. And there's a number of different ways that they can control opening and closing. And then finally, I'm going to end on a very, very important equation that we're going to come back to over and over and over again. And it's what I call the biochemist view of ion channels. And what you're going to see is that ion channels are essentially like enzymes, and we're going to think of them just like enzymes, which I think makes understanding what they're doing and how they're working actually much simpler. And the only difference really between regular enzymes and channels is the fact that, regular enzymes, if you have an enzyme that is catalyzing a reaction such as between A and B, you produce a molecule B, and you think, well, okay, so that's some kind of biochemical, that's some kind of chemical, and it goes off and does things. In the case that we're going to be talking about, this is going to involve the transfer of ions across cell membranes. And the consequence of that is actually to change the membrane potential, which affects the whole cell, right? So that's where things get a little bit more complicated, and we have to introduce a few new ideas. But really, it's essentially, we're going to be viewing this largely from an enzymatic standpoint, from thinking of channels as enzymes. So by way of review, I went through this before, and I pointed out, as we know, right, that because membranes don't allow ions to go through, as a result, you can actually have large gradients of ions across the cell membrane. We know there's lots of potassium on the inside, very little on the outside. We know there's lots of sodium on the outside, very little sodium on the inside, etc. Right? So there are gradients. And then we considered what happens in the event that we have a gradient. And we considered the gradient of a potassium gradient. Then we considered what happens when a selective channel, a channel that's selective to only potassium, actually opens. Okay, and so this is like a water channel, right? Only allows water to go through. And so specificity or selectivity is a key idea, okay? Because we know, as I've just said, there's lots of sodium here on the outside and a little bit of sodium on the inside. But that doesn't really matter. If we have a selective channel, we actually don't need to worry about sodium. We only need to think about the potassium because of the selectivity, right? The only thing that's going to be able to go through this channel is going to be potassium, okay? So now I'm representing this here as X. That can be any channel, but we're just going to review again the potassium. So we're going to start off by imagining there's no membrane potential, and we'll see that means that there's no net charge inside the cell, which means that the net charge in here is 0, which means it's electroneutral, right? And all that means is that there's as many positive ions as there are negative ions within the cell. Okay, that's how we're starting. And now we're asking the question, what happens if we have this gradient of a lot of potassium here and very little potassium here? And we know what the answer to that is. It's mass action. And you're going to get potassium ions going in this direction and some potassium ions going back in this direction, right? But the overwhelming movement is going to be from inside to outside. But here, different from water, every time a potassium ion, for example, this one, leaves the cell, what it does is it takes with it a positive charge and it leaves behind a negative charge, right? It's no longer an electroneutral. A second potassium leaves and you leave behind a second negative charge and so on. So we're slowly building up the charge difference. We're slowly building up negative charge on the inside and producing more positive charge actually on the outside. So the inside of that cell is going to start to become electroneutral or electronegative, right? It's going to be negatively charged ions are actually going to be there. And so that negative charge is going to tend to prevent potassium ions from actually leaving the cell, of course, because there are ionic force or electrostatic forces that are essentially now going to try to pull in the potassium ion back into the cell as it actually tries to escape. So you get to a point where enough positive charge builds up outside here relative to the inside that now the force that's created by that electric field or that difference in potential matches exactly the tendency of the ions to be actually going from inside to outside due to mass action. And we call that equilibrium is described by the Nernst equation. So it's the condition where the membrane potential equals the calculated Nernst potential, which is always referred to as E. And in this case, it's a K, but if we were talking about any ion X, we would put an X here. And that reversal potential, or that Nernst equilibrium potential, is determined by, you can see here, KBT, and you should remember what that is, right? That's the average energy that's available for any degree of freedom, divided by the valence of the ion. In this case, that's 1 for potassium. And E is the electronic charge, right? The actual valence of the potassium ion, which is 1.6 times 10 to the minus 19 coulombs, it turns out. And we'll come back and talk about that. So that's just a number. Turns out that this particular ratio at 300 degrees Kelvin, because remember, this has to be an absolute temperature, is about 25 millivolts. Okay, and that's actually shown here. Okay, and again, in this case, Z is 1. Okay, and then that 25 millivolts, you see it's got the units of voltage times the logarithm of the ratio of the concentration on the outside to the concentration of the ion on the inside. In this case, we have a lot of potassium on the outside, or little potassium on the outside and a lot of potassium on the inside. And we can actually convert this into the log of the base 10 to make it a little bit easier for doing calculations. And it turns out that if you take the natural logarithm of a quantity such as X, and you want to use the log to the base 10, the natural or the base 10 logarithm, turns out that that's 2.303 times the log to the base 10 of X. So when you take that into account, this 25 millivolts per Z becomes 58 millivolts times the natural log, or the logarithm to the base 10 of the ratio of these concentrations. Okay, and that's what determines the equilibrium potential. And in this particular case, if we actually were to do this calculation for potassium, what we would find is the numbers would look something like this. So we would get EK is equal to, now I'm going to use the logarithm to the base 10, be 58 millivolts times log to the base 10 of the concentration of potassium on the outside divided by the potassium on the inside. And we know that this is actually going to be 58 times log to the base 10 of about 5 divided by 140. Okay, and when you take the logarithm of this, you're going to get a negative number because the logarithm of something that's less than 1 is a negative number. And it turns out that that's going to be about minus 85 millivolts. To do a simpler calculation, if we actually had a condition where the outside potassium was, let's say for argument's sake, 10, and the inside potassium was actually 100, millimolar. We would then find that EK would be easy to calculate now, and that's why I like to use the base 10, be 58 times the logarithm of 10 divided by 100, which is actually 58 times the logarithm of 10 to the minus 1, which is actually 1/10. And the way you can work these logarithms is that you can take this exponential and now multiply it by the factor in front. So this becomes minus 58, and log to the base 10 of 10 is just 1. So that then becomes minus 58 millivolts, which is kind of close to minus 85, right? Which is, and you can see that the gradient is smaller here because it's 10 over 100 as opposed to what it really is in a real cell, which is 5 over 140, okay? So that's the use of that particular equation. It's very straightforward, but this is actually telling us immediately, right, what the equilibrium potential is. Given the concentration gradient of potassium across the cell, we can now calculate what the actual equilibrium potential is actually going to be. Now, to apply that information, I want you to think about this particular type of a diagram. And so what you're seeing here is for potassium. So we could do it for any ion, could do it for sodium, and I'm going to do that in just a moment. But you can see here that here's the equilibrium potential. And notice that here we have the current, which is really the flux, right? It's the flux times the charge per particle, right? Because the flux is the number of particles per second. We then multiply by the charge per particle, we get charge per second, which turns out to be current. We'll talk again about that. At minus 85, that's the condition of equilibrium. That's where this is equal to EK, right? And again, that's going to be a situation where we've got about 5 divided by 140 millimolar. When you work that out, it works out to be about minus 85, a little bit more negative than that actually. But notice here that if I actually start at 0 millivolts, what do I have? Well, I actually have an outward current. And that's exactly what we were saying, right? Because we said that in this situation, when the voltage is 0, I'm getting a net movement of potassium from the inside to the outside. That's what that number is telling us. It's positive. And as we're going to go through the convention, turns out that the convention is that if it's a positive ion moving out of the cell, we call that a positive current. So this represents the current, the flux, okay, of positive ions. And whereas if I get below the reversal potential, if I make this inside of the cell extremely, extremely negative, which means that the voltage is very, very negative, in that case, I would actually end up with a negative current, which means the membrane potential or the charge in here is so large that it would actually be pulling potassium into that cell. Okay, and so now we see that this line that we're drawing here is really telling us that if Vm minus Ek, the magnitude of that is telling us what direction things are actually moving in. And if we multiply that by a constant, that's called Ohm's law, we can actually figure out what the actual current is in this case for potassium. So again, if I've got the membrane potential is exactly equal to Ek, we're sitting right here. In that case, that would be 0. So if I now get Ik is G times 0, I get 0 current, and of course that's what this is actually telling us. If the membrane potential is positive relative to Ek, I'm over here somewhere. And if Vm is very negative relative to Ek, I'm down here somewhere and I'm getting a negative current. Okay, so that's the application of these kinds of measurements. Okay, so that's the first review. The second is I want to remind you that membranes are capacitors. And again, what that means is that if I don't have any ion channels and I have some charge separation between the inside and the outside, that charge will just actually sit, turns out, very close to the membrane. Okay, and so when charge actually, as we just talked about, when potassium leaves the cell, let me do it from this particular setting here. again, when potassium leaves the cell, it's going to bring some positive charge out here. It's going to leave behind some negative charge. And that charge is now trapped inside that cell. So when you hit the equilibrium potential, there's a whole bunch of negative charge. The only way it can get out is through the channel. If the channel's in equilibrium, you're not going to get any net current. And now you're stuck with a cell that has a lot of negative charge actually on the inside. And that ability of a cell to create a charge separation between the inside and the outside is exactly what you see with a capacitor, an electrical instrument called a capacitor. And the thing about a capacitor, just like a cell membrane, is that the amount of charge that actually is sitting on the membrane determines directly the voltage between the inside and the outside. So if I want to make a measurement of actual voltage between the inside and the outside, it's going to be directly related to how much charge is actually inside that cell. That sort of makes sense, right? The more negative charge there is in there, so the greater the negative voltage is going to be within that particular cell. And the constant that relates those two is called the capacitance. That's why I referred to, and people refer to membranes as being capacitors. Okay, and so again, I want to emphasize the fact that as soon as you get any charge separation, as soon as there's a net charge inside a cell, that cell will have a voltage, will generate a voltage. There'll be now a difference in energy for an ion on the inside versus the outside. And we already went through that argument. If we have a lot of negative charge on the inside, potassium ion electrically is going to want to go into that cell, right, to meet with that negative charge. And the only reason that equilibrium is a situation where you have a net negative charge on the inside is because our diffusional force is pushing ions out in this direction, but our electrical force, right, because it's now the potassium ions are more stable on the inside electrically, are those two forces will actually again balance. Okay, and so so that's the point, is that a cell voltage means there's excess charge inside that cell. If it's negative charge, it's a negative voltage. If there's net positive charge, that's a positive voltage. Okay. Now I just want to point out as well that the capacitance of a cell turns out to be related to the amount of plasma membrane that actually exists. So in other words, a bigger cell has a bigger capacitance. And therefore, if you make this number actually bigger, what it means is that for a given voltage, if I set the voltage to be fixed, a fixed number, let's say 100 millivolts, if I multiply that by Cm and I make Cm larger, let's say we double Cm, keep this 100. And if we make Cm go from 50 to 100, we would actually find that the amount of charge in this case would be 50 times 100 or 50 times Cm. And in this case, it would be twice that. It would be 100 times Cm. Okay, so the amount, again, of charge for a given voltage is actually proportional to the capacitance of the cell. The capacitance determines the relationship between the amount of charge and the actual voltage that exists. And it turns out that it's actually relatively easy to measure the membrane capacitance electrically. So the net result of that is that it actually becomes quite simple to estimate the size of the cell from an electrical recording, and that's done routinely. And the reason for that is that the membrane has a capacitance per area, which is called a specific capacitance. It's actually a relatively fixed number for all cells. And that number happens to be 10 to the minus 6 farads per centimeter squared. And we'll see what a farad is in the next slide. Okay. But again, maybe I should have done the order differently, but the point is that, charge determines voltage and voltage determines charge. Those are interconnected. And the connection is capacitance, which depends on the size of the cell, okay, the amount of capacitance. So I want to review again some of the conventions that are used in electrophysiology. So the first convention, and some units, okay. So the first thing I want to emphasize is the fact that we measure voltage, and we have an idea, an intuitive idea. We all have batteries, right, for our phones and everything else. And the batteries, of course, create power by storing voltage, right, by storing charge and giving charge a certain voltage. Well, the voltage is actually, by definition, volts is a unit of energy per charge. So it's actually kind of like the driving force. If you got a big energy difference, you're really strongly driving charge from one region to another. So it has units of joules per charge. And what we call the unit of charge is actually coulombs, okay? And like an electron, if we had an electron, you know that that's negatively charged, and we call that an elementary charge. And that elementary charge on an electron happens to be 1.6 times 10 to the minus 19 coulombs. So obviously coulombs is a very large unit. You know, there's like 10 to the 19th electrons in a coulomb, right? So it's a massive number. But anyway, those are the units. And we'll see when we do a couple of problems, right? How we'll do some problems and incorporate things like elementary charges here in just a moment. Okay, that's the first thing. Second thing is, when we measure voltage, we always measure it from the inside of the cell relative to the outside. So actually, the outside is by definition 0 volts. Okay, and that kind of makes sense, because this is sort of the outside of the cell is essentially the rest of the world, really. And so the rest of the world is pretty electroneutral. And so we're always going to reference the voltage relative to the outside. And so the V on the inside minus this V on the outside is what we're going to call the membrane potential. And we're just going to call that Vm, okay? And that's the standard notation, is to call the membrane potential Vm. And again, it's the voltage on the inside minus the voltage on the outside, which is 0. So it's essentially, the voltage is essentially the voltage of the membrane is essentially the voltage on the inside of the cell, okay? All right, and just to give you some numbers, the typical voltages that you see in living systems that you're going to be able to observe are anything from about minus 90 millivolts to about plus 60. You rarely see cells that have membrane potentials that are outside of that particular range. And there's a very, very good reason for that, as we'll see as we move forward, okay, when we talk about action potentials. There's very, very few transporters and phenomenon that can take the membrane potential below minus 90, and virtually nothing can take things above about plus 60 due to a number of factors. Okay, so now let's just get an idea of how big these numbers are. So let's imagine that we have a cell that's sitting at its equilibrium potential for potassium. Well, that's about minus 85 millivolts. Let's ask the question, how much energy does a potassium ion, how much does it change if I take a potassium ion from the outside and bring it to the inside? Okay, so it's coming into a cell, right, that has lots and lots of negative charge. And I forgot to mention in the last slide that all that excess charge, and it is mentioned actually in lecture 9, all ends up immediately underneath the membrane, okay? And that actually ends up attracting an equal amount of positive charge on the outside of that particular cell. And that's what actually sets up the voltage, right? We've got this difference in charge sitting just across the cell membrane. Okay, now the question is, how much energy does what's the energy difference between a potassium ion sitting on the outside around this positive charge, and you bring it to the inside and allow it to interact with all this negative charge on the inside? And it's quite easy to do this because we know that voltage is just joules per charge. So all we need to really do is just multiply the voltage times the charge of a potassium ion, okay? And so the charge on a potassium ion, I've already told you what it is, right? It's an elementary charge, right? It's got a single electronic charge like that of an electron, but it's positive, right? It's not negative. So that's actually 1.6 times 10 to the minus 19. If I multiply that by 85 millivolts, and remember it's minus 85 millivolts, that's going to give us a number which is minus 1.4 times 10 to the minus 20 joules. Now that number doesn't mean very much. The important thing is it's negative. Okay, that's the first important thing. Negative means that it's actually lower energy, which makes sense, right? It's going from positive outside to negative inside. So it should be a lower energy. And that's what this is saying. It's a negative number. Now the magnitude of this number, I told you before, kind of the energy doesn't mean much unless you compare it to KT, which is the amount of energy that's actually available. When you actually work out KT for something that's about 300 degrees Kelvin, which is kind of our body temperature, it's a little bit below the body temperature, but to a good approximation, we'll just call it 300, right? That number turns out to be 4.2 times 10 to the minus 21 joules. So you can see the difference between these. And I've taken the ratio here of the amount of electrostatic energy difference. Okay, that's this number, divided by the amount of energy that's available. And you get 3 times minus 3.3. So that's telling you that the amount of energy that the ion drops when it actually goes in is about 3.3 times the amount of thermal energy that it actually has. So that's a pretty big drop in energy, right? As it actually goes into the cell. Okay, so, and remember that this cell, when it's going down in energy, is actually in equilibrium. And the reason it's in equilibrium is because there's so many more potassium ions on the inside that there's, even though the energy is much lower, the mass action is forcing them out. And we are now sitting in a situation where they're balanced perfectly, and that's the equilibrium. Right? And that's how much of a drop in energy must take place in order for you to overcome the tendency of these ions to want to actually leave the cell. Okay, so those are the conventions. Those are some numbers. And now let's talk a little bit about the current conventions. So first of all, current is measured as charge movement per second. Okay, and we call that IM, not VM, but IM. And we can either use big I or little I. And we'll see that when we use little I, we're talking about single channels. When we use big I, we're talking about whole cell. We're adding up all the current that's coming from all the different ions. And we measure current in terms of something called amperes. And amperes is current per second, or charge per second. And of course, charge is coulombs. So coulombs per second, a coulomb per second equals an ampere. And to give you some numbers, a typical ion channel when it opens up is going to give you about 2 picoamps, which is about 2 times 10 to the minus 12 coulombs per second. And I'll tell you that that's in the range of about 2 million, when you work it out, ions per second. This will be part of your homework for assignment number 3. You'll actually do these kinds of calculations. Okay, and then here's the important thing I want you to remember. You just have to memorize this. Positive current is by definition the movement of positive charge going out of the cell. Okay, so if we go back to this diagram, okay, when we actually write positive current here, this is positive. We're talking here about current that's actually leaving the cell. This is positive charge going out of the cell. And that makes sense. We already said that at 0 millivolts, potassium is on average leaving. That's positive charge leaving the cell. Sure enough, this is a positive number, right? Whereas if we were below the reversal potential, we're in the negative range here, which would represent positive charge going into the cell, okay? So it makes sense, right? We've actually already touched on exactly this convention. We've already used it actually, right? But that's the convention you must remember. Okay, now when we do measure current though, sometimes we just measure it as coulombs per second, but sometimes, which is an ampere, but sometimes we actually normalize it by the area of the membrane. Or more frequently, we just normalize it by the capacitance. Because remember, I told you the capacitance is proportional to the area of the membrane. So if you kind of want to know how much current there is, if I have a cell that's twice as big as another cell. What I really want to know is how much current there is per unit area. So what typically you do in an electrophysiological experiment is you measure the current in a cell, for example, and then you divide it by its actual capacitance. And that then gives you an idea of how big it is relative to all the other cells, regardless of their size, right? Tells you something about the density. Okay, so now let's start to apply some of this information. So the first thing we need to do is learn some definitions. Okay, and the first thing is that, we're applying this and we're going to think about things like excitable cells. An excitable cell would be something like a cardiac cell or a muscle cell or a nerve cell or a beta cell of the pancreas. There's many, many excitable cells in the membrane. The bottom line is that they become active. Excitable cells become excited when they become depolarized. And almost all of these cells, there's only one exception that I'm aware of, and I'm not going to mention the exception, I'll just give you the rule, is that cells, when they go from negative on the inside to positive on the inside, they go from rest to action. Okay, so a resting cell is at a negative membrane potential by definition, pretty much by definition, okay, by observation actually, okay. And typically, so inactive cells are negative membrane potential, and we call that negative membrane potential the resting membrane potential because the cell's resting. And cells, excitable cells, spend most of their time at the negative membrane potential. And only when they're told to do something do they depolarize and then act, right? Like a cardiac cell gets depolarized, which means it becomes positive on the inside. Then it contracts, or it releases neurotransmitter, right? If it's a neuron, or it releases hormone, right? If it's a beta cell in the pancreas, for example. Okay, so these are excitable. And it's with depolarization, when the membrane potential becomes positive, that's called a depolarization. And when it depolarizes, it goes into action, these cells. Okay, and so we call this process of going from a negative membrane potential at rest to action, depolarization, followed by it going back to the resting membrane potential, which we call repolarization. That process of going from rest to depolarization back to rest is called an action potential. Okay, and that's what drives processes. So when excitable cells develop action potentials, that causes them to take some sort of action, right? To become excited and to perform work, etc. And essentially, the point I'm going to make is the fact that essentially APs and excitable cells are really oscillators. And what they're really doing is this resting membrane potential is kind of close to EK. And this depolarized potential is actually quite close to E sodium. Okay, and if I were to watch this, if this were a cardiac cell, you would find about 2/3 of a second later, it would fire another action potential. And then it would fire another action potential. It's just an oscillator. It's basically going from EK to E sodium, back to EK, back to E sodium. It's basically oscillating. So it's really oscillating between a condition where the potassium channels are open and then the sodium channels are open. And the potassium channels, when the potassium channels open, you actually close the sodium channels. And when you open the sodium channels, you actually close the potassium channels. And then you close the sodium channels, and you reopen the potassium channels. And essentially, we're just bouncing between this reversal potential and this reversal potential. Not exactly, but essentially that's what goes on in all excitable cells. Okay, so somehow nature has set things up so that in a cell, we can go through a sequence. And the sequence that we can go through is essentially this following sequence. We can go from a cell that has potassium channels open, and it's negative. And then it goes to a condition where sodium channels are open. And by the way, sodium channels here are closed. It goes to sodium channels open and potassium channels closed. And then it goes back to this state again, and so on. It just goes in a circle over and over again, okay? So that's what cells do. And what they don't do is have a situation very often where both channels are open at the same time. But what we're going to do is very briefly consider what actually happens when both channels are actually opened at the same time. And in this particular case, we're considering a situation. So real cells essentially go from this conductance to this conductance, back to this conductance. And the conductance, I'm just using the term conductance to say channels are opened, okay? So we're going from potassium channels being open here, then they shut off, then these channels open. And we'll see why the sequence goes such as I just described. And here's why, okay? So let's imagine that we actually start off with cells that are actually at the are in a depolarized state, okay? Let's imagine that they actually start here in a depolarized state, and we shut off all the sodium channels, okay? So now we're in a situation where we've got lots of potassium, we've got a positive membrane potential, positive charge in here, and we've got negative charge on the outside. And now what we're going to do is shut the sodium channel and turn on the potassium channel. Well, we've done this already. What happens? Well, potassium leaves, and leaves for two reasons. One is the membrane potential is pushing the potassium out, and the gradient's large, right? There's very little potassium out here. So we have a huge current, right, starting here. Now, if I've got positive charge moving out of the cell, we know what happens. You leave behind some negative charge. And so you're going to tend to move the voltage in this direction, of course, because you're losing potassium ions through this channel. Okay, and of course, if we get to this point at zero, we know that there's still outward movement of potassium. So there's still potassium on average moving out of that cell, which means positive charge is leaving, which means it's still moving in this direction. And we get here and it's still moving in this direction because it's still positive outward current here. And then what happens when we get to this point? Well, at that point, we have an actual balance between the membrane potential and the voltage. We have no more current. So the membrane potential can't change. If there's no current, right, there's no charge moving in and out of that cell. And if there's no charge moving in and out of the cell, the voltage can't change. So that's where it stops. Okay, now imagine that we do the opposite. We shut these channels off and we turn a potassium channel on, or a sodium channel on. So let's just do that now. Let's do the reverse. I know this is a little bit belaboring the points here, but now we're starting at negative potential. We're shutting off the potassium channels and we're turning on the sodium channel. Okay, now we've got lots of sodium out here, very little sodium in here. This is negative. So there's two driving forces here, right? The voltage is pulling in sodium, the gradient's pulling in sodium. Okay, so where are we? Well, we're over here. What's this? It's a negative current. This is negative. Negative current means positive charge going into the cell. Remember, positive charge going out of the cell is positive current. Positive charge going into the cell is negative current. So that's right, we're bringing in positive charge, right? So we're here, we're bringing in positive charge. So what direction is it going? It's going in this direction. Then I get here, or let's say we get to zero, and we considered that situation where there's no voltage across the cell, right, membrane, but we've got a gradient. So we still have positive charge going in. Where's it going? It's going in this direction. And it keeps going in this direction until you get to this point. It stops. Why does it stop? Well, that's equilibrium again. But now it's equilibrium with the sodium channel open. This was equilibrium with the potassium channel open. This is equilibrium with the sodium channel open. And that's basically what happens in an action potential, just bounces back and forth. Okay, last thing I'm going to do on this slide is just mention what happens when the both channels are open at the same time. That rarely actually happens. It does occasionally happen under some disease conditions. And there are, when these transitions are taking place, we have some of these channels are kind of open at the same time. Okay, so in that case, things get a little bit more complicated, but not really that much more complicated. So we'll just consider a case where we have one sodium channel that's open and one potassium channel that's open. Now I'm pretending that these channels have a different conductance. In fact, depending on which potassium channel we're talking about, the conductances are actually relatively similar to each other, actually, it turns out, but they don't have to be, and not all channels are, okay? So, but let's just consider what would happen if we open up these channels at the same time. So now we're thinking about a cell, and we have a potassium channel here, and a sodium channel here, okay? And we could start at any potential that we want, but let's say we started at 0. Okay. Well, what's going to happen is the events are independent, right? Because the potassium channel only allows potassium to go through. So we don't have to think about sodium for this channel. In case of sodium channels, they're relatively specific for sodium over potassium. So we don't really have to think about what's going on in terms of potassium current. We only need to worry about what the membrane potential is and what E sodium is. Here we have to worry with the potassium channels what the VM is and what EK is. That's what's going to dictate how much current. So let's start at 0. You can see what's happening here. Here's the amount of positive charge going out through a potassium channel. We'll give that number a number 2 because it's 2 picoamps, let's say. And we look at the sodium channel at 0, and what do we get? Well, it looks like it's about 1. So that's 2 minus 1. Well, you can see the net charge. There's more distance here. This is a bigger positive number than this is a negative number. So if I add those two together, I get about 1 picoamp of positive current going through here. Right, I'm going to end up with essentially, what's the difference between this and this? Well, it's right about here. Well, that's an outward current. If it's an outward current, if we started at 0, it's an outward current. That means on average, the net is going to be, there's going to be some sodium coming in here, but there's quite a bit more potassium actually leaving this cell. So the cell is going to become a little bit negative. So it's going to move in, the voltage is going to move in this direction. Of course it is. And then what happens when it comes over to this point? Well, I can just do the comparison. And I see here that this is still a little bit positive. If I were to take this number, it might be 1.5, and this might be now minus 1.3. But I still have a net positive current. So I'm going to end up going a little bit further over. I'm going to get to a point at which this distance is exactly the same as this distance, right? We're going to call this maybe 1.4 minus, and this number minus 1.4. And lo and behold, they're plus 1.4. And the sum of those two is 0. So in this particular case, I would end up going to that particular voltage. That's not an equilibrium voltage. I've actually got as much potassium leaving this cell as I have sodium coming into this cell. That's called a steady state, okay? And that membrane potential will not change because the net current that's going through that membrane at this particular point is actually 0. Okay, so at this particular point, I'm actually at the point, I'm in a condition where I, potassium, is exactly equal to I, sodium. The negative, of course. The negative of this becomes, so the sum of the I sodium plus the I potassium equals 0. And when you solve for that, this is the way we write the equations, right? It's a conductance times the difference, right? The driving force. The conductance times the driving force. And notice here, VM is the same, of course, because the channels are in the same cell. But E sodium is different from E potassium, right? E potassium is minus 85. And E sodium is about plus 60. Now we can solve for VM. this is just one equation with one unknown because EK and E sodium are fixed. G sodium and G potassium are fixed. That's the molecular structure of the channel. You can solve that and you can determine what the membrane potential is for the condition of zero current. I just set this equal to 0. I solve for Vm and I get that it's essentially the weighted average of the conductance times the reversal potential. Okay, I just have a little note here to say that the I versus V here, is drawn as a straight line. There's no straight lines with channels, but it's a very, very good approximation. And I'm just going to make a statement here. Near equilibrium, it's always true for all transport processes. When you talk about Van 't Hoff's law, or you talk about ion channels, ions going through ion channels, at or close to the equilibrium potential for those phenomena, regardless of what kind of transport you're talking about, the system will always become linear. So this approximation, this equation that we're writing, might not be true for all voltages, but near the condition where Vm is equal to E sodium, it's absolutely true that there'll be a linear relationship between these two parameters. Okay, so let's go on to the next slide. Okay, so now my pen is doing something funny, something funky again. So let's see if I can't, let me just stop this for just a moment. Okay, so now let's start to apply this information even a little bit further. And we're going to consider 3 different questions. First question we're going to ask ourselves is, what happens when many channels are of the same type are actually open? So we just considered the case where one is open or the other is open. And then we briefly just went through the situation, which doesn't happen all that often, at least not for long periods of time, where two types of channels with different reversals are open at the same time, right? And what we found is the membrane potential is going to go to the point where the current is 0, right? Just like if a selective channel opens, it's going to go to its reversal potential, which happens to be the equilibrium potential, which also happens to be 0 current. Okay, it's always going to go to the 0 current condition, right, and stay there because then things can't change. Okay, now we're going to consider what happens when multiple channels open. We're also going to ask the question, what controls the opening and closing of channels? And this we're going to spend a fair bit of time on, actually. And then eventually we're going to go towards and understand the basis of selectivity. Why is a potassium channel selective over sodium ions, for example, or sodium ions over potassium? And in answering these questions, we're going to spend a fair bit of time looking at the molecular structure of channels. Okay, we're going to start by just considering what happens. Why is it that we have so many channels inside cells? And just to give you an example, cardiac cells, typical cardiac cell has about 3,000 voltage-dependent sodium channels. It has about 10,000 potassium channels. Some voltage-dependent, multiple types. Some not voltage-dependent. We'll come and talk about non-voltage-dependent channels in a moment. And then we've got about 40,000 calcium channels in the cardiac cell. Lots and lots of calcium channels. So what happens? Why are there so many? And I just want to illustrate what happens when many channels open. So we considered the case where we just have one channel that opens. Okay, and we wrote the equation, GK in the case of potassium channels, because this is a potassium channel, is Vm minus EK. Always the same kind, right? This is essentially Van 't Hoff's law. This is the driving force here, and this is just the conductance, right? A number. It's actually a number. And that's giving you the amount of current. Well, obviously, if I have 2 channels, I can put a 2 here. Or if I have 3 channels, I can just put a 3 here, and so on. Now, remember, however, that if I have a cell and I have 1 channel, I get a certain amount of flow. Let's say we're talking at 0 millivolts. I'm going to get a certain amount of potassium ions going into this cell. If I have another channel, I'm going to have twice the number of ions going into that cell per second. So what that means is that my membrane potential is dependent on how much charge is actually inside that cell. So if I open up 4 channels, I'm going to change the membrane potential 4 times more quickly than if I have just 1 channel. So multiple channels, when we're talking about particularly potassium and sodium channels, is all about speed, right? It's all about making that membrane potential change very, very quickly from one value to another. Remember that when you are doing this activation process, you also have to spread that depolarization. Now, we're not going to get into those kinds of details, but those are processes that actually sort of dilute out the current that's actually going in. And so to make things fast and sure, what you need is lots and lots of channels. So this is just an application of our equation, right? Which is this equation, which is what I'm going to call the single channel equation. This has essentially got the thermodynamics built into it, right? We see the reversal, we see the energy. We see the energy here, and we see the mass action term here. This is essentially the thermodynamics. It's telling us what direction. Now, I said to you already, ion channels are essentially enzymes. And enzymes don't change the direction of the reaction. All they do is change the speed. So what we're doing when we turn a channel on is these are numbers that are determined. All we're doing is just changing the conductance. We're opening up a channel. So now things can actually move from one side of the membrane to the other. That'll become more obvious in just a moment. Okay, so a little bit about techniques. So there's really 3 techniques I want you to be at least aware of. One is the sharp electrode technique, where you actually just have an amplifier and you take this electrode and you shove it through the membrane without damaging it or causing minimal damage. And you can now compare the voltage inside that cell to the voltage outside the cell. And now you can get a measurement of VM. Okay. Now there's another kind of technique that's referred to as a voltage clamp. And before I talk about the voltage clamp, I'll just talk about the patch clamp. So patch clamp is where you can take a glass electrode, and if you polish it and treat it in just the right way, it'll actually form a very, very tight seal with a membrane. And that allows you to do a number of things. It allows you to isolate a single channel underneath the membrane, inside the pipette in the membrane. You can actually rip that piece of membrane off. This is called a cell attached patch single channel recording. You can rip that off. That's called a ruptured patch single channel recording. Or you can actually disrupt the membrane completely and just gain access into this particular cell. And in all 3 of these cases, you're actually able to measure current while controlling the voltage across the membrane or within the cell itself. And that's referred to as a voltage clamp. Okay. So most of the stuff I'm going to show you is a voltage clamp recording, right? A voltage clamp recording using a patch clamp technique. I've spelled it wrong here, but it's patch clamp technique. Okay. And you can review this at a later time, and so you have some feel for how these measurements are actually made. Okay, so now we're going to spend a fair bit of time actually talking about what controls channel opening and closing. Okay, and the first thing I want to emphasize is that these are isomerization reactions. Think about it, right? We're thinking about a potassium channel. We're saying the potassium channel can be open or closed. Well, that's just like saying, you can have a cis trans, right? It's the same molecule, but it's just a different structure. And that's what we're talking about here when we talk about ion channels, right? When they're open, they're a different conformation than when they're closed. That is an isomerization reaction that we're actually talking about. So here's an example of a potassium channel. And I know it's a potassium channel because here's the negative charge on the inside. So this is a condition where VM is negative, and this channel is closed, okay? Actually, when I think about it, it could be a sodium channel or a potassium channel. So let me just back up, okay? So this is a negative membrane potential, and we have the channel that's actually closed. When you depolarize the membrane, you actually are now putting positive charge on the inside. I don't know how it got positive. I could have done it with the amplifier. It could have been that current went into that cell. But now you see that the channel actually is open. And now ions can actually go through that particular channel, whether it's a sodium channel or a potassium channel. So essentially what we have here is, as a function of voltage, depending on the voltage, the channels are actually going to be in a closed state or with negative membrane potentials, or they can go into an open state at positive membrane potentials. And that's the general rule for voltage-dependent channels, is they open with depolarization. Now, there are potassium channels and other channels that are not voltage dependent. And in that case, some of them are opened all the time, or they're opened without necessarily being sensitive to voltage. Okay, and those are called background currents. And we'll come back and talk a little bit about those as well in a bit. But right now, we're considering the isomerization reaction, which corresponds to channels going from closed to open. And the general rule is that voltage-gated ion channels will go from a closed state to an open state following depolarization. When they get excited, they open up channels, okay? And we'll see that there's a sequential, that this is actually a sequential process. And I'm going to make the point again that this closed open change in conformation is an isomerization reaction. Of course it is. And the kinetics of opening and closing, right? Whether they're open or closed depends on the membrane voltage. And opening, is, we call that, the process is called channel activation. And we represent this closed opening transitions. We call that channel gating. But it's nothing more than chemical kinetics, right? We've already talked about, this is a KCO, and this would be a KOC, right? This is the rate constant for going from the closed to the open state. This is the rate constant going from the open to the closed state, right? It's, again, an isomerization reaction. Now, there are other kinds of channels. We talked about them, right? Different kinds of classifications. And one of the other ways to classify channels is on the basis of what causes them to open and close. And here's an example of ligand-gated, right? These are channels that when they bind a ligand, when they bind a molecule, the binding energy of the molecule gives the channel enough energy to cause it to go from a closed to an open state. And again, this would represent a closed state. This would represent an open state. And in this case, these rate constants are dependent on the ligand rather than the voltage, right? Although there could be a voltage dependence as well. And here's a typical voltage clamp experiment, okay? So in this particular case, see if I can blow this up a little bit. In this particular case, we're going from a very negative membrane potential of minus 100, and we're stepping to approximately plus 50 millivolts. So that's, again, going from closed channels to open channels. And you can see that that's indeed the case. Now, this is a single channel. So now you can see a couple of things. First is that before the step, which is at this line here, there's no current. These lines here. This is a repetitive, this is a situation where we have a patch with a channel in it, attached to a membrane, probably attached to a cell. And now we're just repeatedly applying a voltage across this patch, okay? We're going from a negative to a positive cell. And every time we do that, we're getting essentially this process taking place, right? Channels going from a closed to an open conformation. Okay, and you can actually see what happens here. And they don't behave the same way because it's a single molecule. So it's getting knocked around by thermal energy. And so, but on average, as soon as you depolarize, they really like to undergo excursions from the closed to the open state. So here we're closed, and now we're actually going to the open state. Not all the time, right? Like here, it stayed closed for quite a while. Then it opened, then it closed again. And eventually, of course, we repolarize back to minus 100. And you can see that all the channels actually are closing themselves off. And this is the behavior if you add up. So this is repeating the same measurement on the same channel, okay? Over and over and over again. You repolarize, then you depolarize. You repolarize, you depolarize. And each time you depolarize, you get a different sort of behavior. That's called stochastic behavior because it's a single molecule that we're actually observing. And this, if you add up maybe 20 or 30 of these, This is the average behavior you actually get. So if you did a whole cell recording and you had a bunch of channels in this membrane all at the same time, this is what you would actually see. But you see exactly the same thing if you actually look at one channel and you just look at it 100 times. It's going to behave just like a whole cell that has 100 channels. So this would be the equivalent of a whole cell recording, but it's really just the sum of single channel measurements, right? And whether you do a whole cell, basically adding up the average behavior of all the 100 channels, but that average behavior turns out to be exactly the same as if you looked at the same channel and just measured it 100 times, okay? That's something called an ergodic principle that is true in all chemical systems, actually. Okay, now not all channels just have a closed and an open state. For example, a sodium channel also has a third state, a third isomerization conformation, right? So it's got a closed conformation, it's got an open conformation, and it's also got an inactivated conformation. So just like the example I showed you before, if you're at a very negative membrane potential, channel's in a closed state. If you now depolarize the membrane as shown here, that channel becomes open. And now while that channel is actually in the open state, in this particular case, in the case of the sodium channel, you have some other conformational change that's actually happening. The channel's activated by the voltage, right? So it's gone from the closed to the open state, but now it's in a non-conducting state because something else has actually moved into the pore or some other conformation has changed, causing it to go to an inactivated non-conducting. Okay, so this is conducting. Right? This is when you've got the GK or the G sodium or the G calcium term is actually is in place. And this, of course, is also non-conducting, right? Because if it's not open, it can't be, there's no G, there's no conductance actually occurring there, okay? And we refer to that as inactivated. So the way we represent that, it's an isomerization reaction, but now we have to think about 3 different states, okay? And we're going to have a Python program that actually, there is a Python program already up that is actually solving this particular configuration. And here's what you would see in a single channel recording, and this is what you actually do see in single channel recordings of sodium channels. I've missed out on the voltage clamp here, but it's actually the same voltage clamp experiment I showed before, minus 100 to about plus 50 or so. Okay, and now what you see is, let's not worry about this one here, but let's look at all these other transitions. And so you see these channels are going from the closed to the open state, closed to open, closed to open. But you'll notice that after they open, they close, even though the cell is still depolarized. Okay, this membrane is still depolarized at plus 50. And now the channel has gone into a non-conducting state. What's happened here is that with the initial depolarization, they transition into the open state, and then they quickly go into the inactivated state from which they basically sit for the remainder of time. And so when you look at a whole cell recording, you add up a whole bunch of these events, or you record from 1,000 of them at the same time or 100 of them at the same time. Here's what you would observe. Inward current, followed by the decay of that current. Okay, and this is the inactivation process. This is the channels going from the open to the inactivated state. This is closed to the open state. Okay, and again, there's a Python program that's available that you can play with that actually demonstrates this. Okay, so I got rid of all my stuff here inadvertently. Okay, now I don't really know why I'm not at the end of my lecture yet, quite yet. Okay, now is the time for me to introduce a very, very important equation. Okay, and that equation is the one that's actually shown at the very top. So if I want to know the total current, oh, I see what's happened here. I have to actually just stop this presentation for just a moment. Okay, so I don't know, somehow I've changed the orientation of my slides. I'm not going to screw with it because I could lose everything. So, um, okay, so this is the slide I was on. Okay, so see if I can get my pen back. Okay, here we go. All right. So here's the important, oh my God, I just did it again. I got to stop. Sorry, folks. Okay, anyway, this is my new system, my new iPad system, which is way better than the old system. But anyway, I still have a few hiccups here. So I'm a little afraid that I'm going to lose everything because it's happened already once since I tried to do this lecture. Okay, anyway, to get to the point. So what I want you to appreciate is this particular equation. It's an extremely important equation, and it's essentially the biochemist's view of the way ion channels actually work. And here's what it says. It's very intuitive that the total amount of current, so that's essentially like the flux through an enzyme, okay, is related to three factors. And it makes perfect sense. The number of channels that are actually there, the number of enzymes. If I have 100 times 100 enzymes, I'm going to have 100 times the reaction typically that I'm going to have with one enzyme, right? So the total current is going to be, if I have a cell, total amount of current that's going to go into that cell, it's going to be related to the number of channels that are there. That makes sense. Times the probability of a channel actually being open. I just showed you that channels will transition from closed to open states. Let's just consider that, right? Let's not worry about the inactivated states. They're actually literally bouncing back and forth. And as we'll see a little bit later, we're going to see that the probability, we're going to talk in terms of the probability of the channel actually being open, is strongly a function of voltage. Well, we've kind of already seen that, right? If we step positive enough, we see the channels actually opening. Later, we're going to be able to show that the probability of opening actually looks something like this, where this membrane potential is somewhere, depending on the channel, somewhere around -20 to about -10 millivolts, okay? So it's a gradual thing. That makes sense. It's not going to be an all or nothing thing. As you go to very negative potentials, they're all closed. The probability is zero. If you go to a positive enough potential, virtually all of the channels actually open themselves up, okay? So that's what we're going to find, okay? But once the channels are actually opened, if any channel that's open, if I have 50% of my channels open, I would say, well, really, let's say I started with 100 channels and I have 50% of them that are open. So the open probability is 1/2. I would multiply that by 1/2. That tells me that there's only really 50 channels there. So that would be 50. And now if I have 50 channels, I already told you, if I have 4 channels, I get 4 times the current that I would get with one channel, right? So now if I actually have 50 channels, I'm going to get 50 times the amount of current that I would actually get with a single channel. And that's all this is saying, right? It's saying the number of channels times the probability of them being open times the amount of current that a single channel produces is going to give me the whole current, the whole cell current. That's the total current that you're actually going to observe. That makes intuitive sense, right? And this is the enzyme. This is a single enzyme. If it's operating, it's going full blast. It's going to catalyze anything that wants to come through its pore. It's going to allow. It's operational. But if I only have 50% of them that are operational, I have to scale by the probability of a channel actually being open. We know that for enzymes, right? The same thing. They're regulated. They're not always on. They have all kinds of allosteric regulation. Same thing happens with ion channels, okay? So this is the single channel behavior. That's this term, right? And we're going to talk about how, and there's a Python program that's going to actually, solve these kinds of problems for you. And we'll talk more about those, right? So we've got the gating schemes that we're going to be using. That's going to tell us the open probability. We're going to solve these kinds of equations, these chemical kinetic equations, and we're going to solve for the likelihood of a channel actually being in that open state, because that allows us to get the open probability, right? If I've got 50% of my channels that are in this state, 50% of them are going to be operational. They've got their pores open. The other 50% presumably would be either in the closed or the inactivated state. And we'll even sort out, we'll be able to sort out how many of them are in a closed state, how many of them are actually in the inactivated state. Now, for some channels, we only need to worry about closed and open states. In that case, it's actually pretty simple. Very simple isomerization reaction. These are a little bit more complicated because there's 3 states, but there's tools that are used all the time to actually solve these things, and they're actually relatively easy to solve. Okay, so the last thing I'm going to end on is just driving home the point that ion channels are actually enzymes, okay? And why are they enzymes? Well, first of all, they're selective. They do selective catalysis. It's exactly what enzymes, you've been taught enzymes do. Next thing is, we know that enzymes are allosterically controlled and regulated. And the example of this is this, this hypothetical diagram here, where we actually have an enzyme, and here's the product, okay? So we're starting with a substrate, and we're getting a product. And there's the substrate is going to be going in, being catalyzed over a number of steps into the product. And for many enzymes, once the product builds up, it actually binds to the channel or to the enzyme itself, and it regulates the extent to which that enzyme is actually going to be able to produce the product. That's called end product feedback or negative feedback, right? Product, or I should say, product feedback onto the enzyme. You also have some enzymes that have feed forward, right? So if the substrate goes up, it actually turns the enzyme on. That's all allosteric regulation. In our case, our allosteric regulation is done by voltage. The voltage is an allosteric regulator of the channel, okay? Or in a ligand-gated channel, the ligand is the allosteric regulator, right? Because the binding of the ligand is what's turning on the channel, just like in the case of the feed forward, or in this particular case, the example that we're giving here, right? We have the opposite. We're actually saying that, we have a end product that is negatively regulated. That would be like a ligand turning an enzyme off, right? In the case of the ligand gated, it's turning it on rather than turning it off. But we're going to see examples of where, in the case of calcium channels, for example, when calcium goes into the channel, it actually binds to the channel and shuts it off, okay? So that would be a classical example of end product down regulation of the activity, right? And that's going to affect the open probability and shut the channel off. And that's how these systems actually have feedback. And then on top of that, channels also are regulated by, regulatory proteins. And we know lots of examples of that, like protein kinase A. Hopefully you've taken this before in your cell biology. But, protein kinase A is a very, very well-known regulator of activity of many, many different cell types. And it is regulated allosterically by binding to these ACAP proteins, as well as these regulatory proteins that actually then bind to the ACAPs. And it turns out that these things are actually produced or created and put into these large macromolecular complexes where there's all kinds of protein-protein interactions. And we're going to see later that channels are very often found in macromolecular complexes. So they're actually bound to a whole bunch of other proteins that in the case of calcium channels, we're going to see that they actually have protein kinase A. This whole system right here is actually attached to the calcium channels. Okay, so the whole calcium channel is allosterically regulated by protein kinase A by phosphorylation of the channel. And all that stuff is just bound right up to the channel itself, okay? And we'll do examples of that. So anyway, that's the end of the lecture. I will see you again on, there'll be an asynchronous lecture this coming Tuesday, and I will hook up with you again on Thursday. And I already gave you all the announcements and whatnot. Okay, so bye.